All right, let's get started. Welcome, everybody. Sumanth in particular, of course, members of the committee, family of Sumanth, students, faculty, former students at Barna. This is the defense of Sumanth Rotti, and I'll leave it to him to introduce his talk and the title, etc. You have about 45 minutes to an hour, Sumanth, and then we have questions from the audience, as you know. And after that, there's a closed meeting of the committee. Now, I just want to say I kind of missed the little bit tense atmosphere of a college lecture room, but given the circumstances and that it's the middle of summer, this is probably the best way to do. So good luck.
We can make it more tense for someone.
Yeah, we can.
Thank you, Pete. Good afternoon, everyone. I warmly welcome you all to this presentation, which is part of my PhD defense. I have waited so long to see this day. So my doctoral work, I hope you can all hear me well.
Yes, we can.
Okay, thank you. So my doctoral work focuses on the development of a robust model to predict solar energetic particle events. I'm glad to share with you the parts of all my projects and the application we foresee as an outcome of this dissertation. I want to start off with some formalities before I enter the topic. So I dedicate my PhD to the two of most important people in my life. My teacher, Dr. Bananche Govindacharya, an enigmatic scholar in Indian philosophy, and my father, Mr. Anand Tirtha, who trusted me so well and gave me all the freedom in my life. These two have been instrumental in playing a crucial part in my journey, and it is unfortunate that I don't have them physically present with me now, but they're always there in my memory. So I would like to thank Professor Martens for being such a great and kind advisor. Thanks to the rest of my committee members. Professor Manolis Jargolis is an expert in solar physics, and he is joining us from Johns Hopkins Applied Physics Laboratory. Professor Rafa Langrick is from the Computer Science Department at GSU and heads the data mining lab with Pete. Professor Vadim Apolkov joins my committee from the physics, and Professor Fabian Barrel from astronomy. I thank graduate advisors, Professor Murat Sarsour and Professor Russell White for their continued support and guidance. I thank my big-time collaborators, Dr. Barkai Aydin, Dr. Dustin Kempton, and Dr. Azim Ahmadzadeh. CS students, current and former students, Nikhil, Shuman, Akhil, and Annie, thank you very much. Thanks to NASA for funding my research, travels, and publications. I acknowledge the use of data from GOES, SOHO, and SDO missions. Thanks to all the faculty and staff at the Department of Physics and Astronomy. I have had some fantastic and supportive colleagues. Thanks to all of them for helping me at various times. And lastly, thanks to all my friends and family members for supporting me at all stages. Here's a quick introduction about myself for those of you who don't know me. I was born and raised in Bengaluru or Bangalore, a city in the southern part of India. I got a bachelor's degree in physics, technician membership from the Institution of Engineers, which is equivalent to a bachelor's degree in engineering. And then I have a master's diploma in aerospace design. I worked for a little while, over 3 years, while I was in India, initially as a design engineer and then as a researcher at the Indian Institute of Science. When I was 26, I left India to pursue a master's degree in mechanical engineering and management at the University of Glasgow in Scotland, UK. So I moved from Glasgow to Georgia State University. I'll give a brief timeline of my days spent at GSU. So I joined the doctoral program in the Department of Physics and Astronomy in the fall of 2018 and started my journey in solar physics in the summer of 2019. Then in summer of 2020, I cleared my physics qualifiers, gave my prospectus talk, got a master's degree in physics, and completed my project on the EIT flare catalog. After that, I was involved in studying SAP events. In summer of 2021, I received a grant from NASA to support my research. By fall 2022, the SAP dataset was ready, followed by statistical analysis of the data. And later on in fall 2023, I was involved in implementing machine learning in my project to build an SAP forecasting system. So with the completion of my PhD project goals, I am looking forward to graduating from GSU. And today's talk will essentially cover the work I have done in the last 3 years. So let's get started to talk about my research involving the sun. So the sun is a glowing ball of plasma, and it has been a source of life on our planet. There are 3 distinguishable regions: the interior of the sun, its visible surface, and then the solar atmosphere. The solar interior consists of a core, a radiative zone, and then a convective zone. The visible surface of the sun is called the photosphere. And then the solar atmosphere is the coronal region that extends all through the solar system. It is the photosphere and the corona that can be probed using sophisticated observational instruments. So the sun is the closest star that we can observe in such great detail. Other than numerous ground-based solar telescopes, several missions have observed the sun from space. The image here shows solar missions launched and operated by several space agencies around the world since 1960. And so we have a lot of data coming in from solar observations that have revealed several facets of solar dynamics. The image on the left shows the periodic variability of the sun. We have come to understand that the sun is active, and this activity is driven by magnetism. So solar activity has an approximately 11-year cycle that is determined by the number of sunspots. Low sunspot number indicates a solar minimum, and a high sunspot number corresponds to a solar maximum. And a group of sunspots on the solar photosphere is surrounded by active regions with a magnetic field estimated at about 100 Gauss. So the relevance of solar activity becomes prominent due to the space weather effects. Space weather is the stringent influence of solar activity broadly on the solar system. It has several elements. So solar wind is an electrically neutral continuous emission of low energy solar particles. And solar flares are sudden bursts of radiation that appear as intense flash. And coronal mass ejections, or CMEs, are eruptions of solar plasma and magnetic field structures. Lastly, solar energetic particles, or ACPs, are intense radiation of charged particles from the sun that predominantly constitute protons. So when it comes to space weather prediction, I would like to illustrate it using a pyramid to place these different elements so that they indicate the inherent rarity of their occurrences. The solar wind will be at the base, followed by flares and CMEs, while ACPs will stay at the top. So please note that solar wind are always there. So in any given solar cycle, there could be tens of thousands of flares, followed by many thousands of CMEs. However, we have only observed a few hundreds of ACPs near Earth. So space weather forecasters are interested in predicting the speed of solar winds, the magnitude of solar flares, and the characteristics of CMEs such as direction, velocity, and width. And when it comes to ACP, it is the energy of the particles, the duration of the events, and the fluence, which is the flux integrated over the event. So the ACP events and the efforts to accurately predict them are at the heart of my thesis, and I will get into those details right after the next slide. Just to introduce the flare magnitude nomenclature, solar flares are categorized by NOAA using long band X-ray fluxes. It is a logarithmic scale where logarithmic scale from least intense to the most intense flares. And in the image on the right, you can notice a bright flash in light corresponding to an X 5.8 flare that occurred very recently on May 10th, 2024. So to define a strong SEP event, we follow the Space Weather Prediction Center. The solar protons in the 10 MeV channel crossing the 10 particle flux units. And a typical temporal profile, temporal plot of a strong SEP event is shown here. For SEPs, there is a solar radiation storm, storm indicator on a logarithmic scale. So the S1 indicated in the horizontal dashed line is the base level. And the vertical dashed line shows the onset of the SEP event, the moment at which the fluxes have crossed the S1 threshold. So what do we know about the physical characteristics of SEPs? So SEPs are accelerated from the sun. There are two known sources. First is during the reconnection process of a solar flare, and the second is the CME shock fronts. When accelerated from the sun, SEPs travel along the interplanetary magnetic field lines. The particle fluxes are very dynamic, and they can vary several orders of magnitude in a short time scale. The elemental abundances of SEPs show a non-equilibrium distribution of solar particles constituting protons, electrons, and heavier nuclei up to iron. And when SEPs are magnetically well connected to near Earth space, they can cause a variety of radiation hazards. And I'll talk about that in this slide. So the movie on the left is captured by a specialized instrument called a coronagraph. Here, a central disk covers the sun, creating an artificial eclipse that reveals the solar corona. So what we see here is a CME cloud erupting from the sun, followed by an SEP event that hits the instrument, causing the snowing effect. So there was a flare observed first that was classified as X8.2. Following the flare was a CME that traveled face on to Earth at about 3100 kilometers per second, and the measured SEP fluxes crossed 1400 PFU in the 10 MeV channel. There are observed technological and biological effects from high energy SEPs. SEPs cannot penetrate the Earth's, SEPs cannot penetrate the Earth's magnetosphere, but they can get funneled into the Earth's polar region during very intense events. So when that happens, it leads to intense ionization of the polar ionosphere, and the charged particles can affect the signal propagation of communication systems between Earth and satellites. Aircraft taking polar routes can face disruption in the avionics, and passengers on such flights may be exposed to radiation. Nonetheless, the adverse effects are seen outside the Earth's magnetosphere. So SEPs can damage the spacecraft electronics. They can lead to acute and chronic radiation effects on astronauts during travel and extravehicular activities. And extended exposure to charged particle radiation can cause damage to the central nervous system, vision, and heart, and can even lead to cancer and bone loss. Just a historical motivation. So in August 1972, there were solar storms of very high magnitude. So a solar flare of estimated X20, a CME that reached the Earth in just over 14.5 hours, and an SEP event of proton fluxes reaching 70,000 PFU in the 10 MeV proton energy channel. So luckily, these storms occurred in between the safe return of Apollo 16 and the launch of Apollo 17. So just imagine, had the Apollo crew been exposed to this particle radiation of extreme intensities, they should have made an emergency return to Earth for life-saving medical treatment whilst suffering from acute radiation sickness. So what I want to emphasize is that SEP events are of more than scientific interest. So NASA has a lineup of Artemis missions to put humans back on the moon in late 2025. And yet the tackling the particle radiation risk remains a challenge. So the travel time lasts several days, and the extravehicular activities on the lunar surface can last up to 8 hours. Suppose there is a strong SEP event, so then the crew must seek shelter or gather shielding to protect themselves from radiation exposure. So we cannot stop the sun from doing whatever it is doing. So we can only take measures by estimating the probabilities of SEP events. So SEP forecasting has the following purposes: to support mission-based operations outside the Earth's magnetosphere, providing predictions on the arrival of SEPs with sufficient lead times, and to predict the event of a specific magnitude. So we have existing efforts that use physics-based empirical and machine learning methods, and some of the models are computationally expensive, and machine learning generally requires reliable and high-quality data sets. The all-clear forecasters have a longer prediction window, for example, 24 hours or more, but are yet to achieve the desired robustness. And moreover, some of the models that have been implemented in near real-time operations have relatively high false alarms and misses. So the need of the hour is an efficient SEP prediction system that is fast and light. That said, we channeled our project to the following specific goals. First is to generating high accuracy short-term forecasts with lead time up to an hour, and using time series based machine learning models. For that, we wanted to develop a dedicated and high quality data set, and lastly to transfer our model to NASA for operational use. Okay, getting into data. So for efficient machine learning implementation, it is not just the quantity, but the quality of the data is also a requisite. Unless we fix the errors and shortcomings in the data, bad quality can mislead both model and data-driven analysis. So this famous quote, "Garbage in, garbage out," perfectly summarizes the importance of data for operational tools in order to solve the problem meaningfully. That is where the standardized approach of developing benchmark datasets has surfaced largely in the machine learning community. These datasets can serve as a basis for comparing and evaluating different models and methods. When it comes to SEP data, we follow these 3 steps. Collecting the data from existing long-term missions, checking for their format and integrating them, cleaning the data for any errors in the measurements and validating them, and analyzing the data to get insights that are otherwise not obvious and build our experiments. We have the GOES missions operated by the National Oceanic and Atmospheric Administration in the geostationary orbit. So at any given point in time, at least 2 satellites over the east and west coast of the US make parallel observations of the sun. One of them forms the primary satellite, while the other is secondary. So from the GOES missions, we download the raw integral proton and X-ray fluxes and save it on our data repository. Once we gather our data sources, we go to the next step of cleaning them, homogenizing across multiple GOES missions by applying the appropriate correction factors, identifying and removing spikes in the data with moving averages, and filling missing values with linear interpolation. The data cleaning process also involved visual inspection to identify reliable GOES missions rather than considering the data from primary GOES alone. So the result of this inevitably complex, tedious, and least enjoyable part of the project is presented here. If you scan the QR code, it will take you to the repository where you can find and download the data set. So the geostationary solar energetic particle events, or in short GSEP, is a data set consisting of over 400 ACP events that were observed near Earth. The data set spans from 1986 to 2018, and it has a carefully curated catalog and cleaned time series slices for all the ACP events. The GCP is publicly available on Harvard Dataverse for anyone interested in it. And this is an active data set, meaning we have kept it updated and hope to continue to do so. So based on the S1 event threshold defined by Space Weather Prediction Center, the GSEP dataset has 244 large SAP events, so where the 10 MeV proton fluxes are above 10 PFU, and 189 small SAP events with proton fluxes between 0.1 and 10 PFU. For the catalog, we have integrated several information from existing catalogs. The paper shown on the top, it describes the development of the dataset, and there's a second paper about the statistical analysis of the GSEP dataset. Both papers were published in Astrophysical Journal Supplement Series. Metadata. So the metadata in the catalog consists of more than 40 temporal and characteristic parameters of ACPs and the associated solar sources. That is, we have tried to identify as much source information as possible, such as active regions, flares, CMEs, and type 2 radio bursts. Whenever there is ambiguity in the source association, we visually inspected observational data and corrected them. And we have extensively consulted multiple data sources during a source association. The time series slices are derived from event definitions provided in the GSEP catalog. The subsamples are separated across the solar cycles and saved in the repository. So we include 12 hours of observations prior to the ACP event onset in each time series. The end time of an ACP event is typically when the proton fluxes fall below the corresponding threshold. And the GOES proton data has a 5-minute cadence. So each data point in the time series represents a 5-minute interval. In the next 4 or 5 slides, I'll briefly present you the results from the analysis paper. Excuse me. Here is the distribution of the ACP events in the last 3 solar cycles. So we can clearly see the pattern following the solar activity with more ACP events observed during solar maximum and fewer during solar minimum. And furthermore, solar cycle 24 was relatively weaker compared to cycle 23 and 22. Next, okay, we find that the average rise time of ACP events is about 11.5 hours. Rise time means the time from the event onset until it reaches the peak flux level. When we further analyze, we find that ACPs associated with halo CMEs have a slightly larger rise time of about 13 hours, and non-halo associations have less than 10 hours. Rise time statistics are important because they help us estimate the event fluences necessary to understand the possible particle radiation dose rates. Moving on, we find about 80% of the ACP events in our data set arise within 12 hours following a source eruption. Talking of source eruption, out of our 400 and more ACP events, 383 ACP events are associated with a solar flare, and the distribution of these flare classes is shown here at the top right. The median flare class for a large ACP event is M2.0, and in addition, the flaring sites on the sun are strongly populated from the central to the western hemisphere. Next, we have 247 CME SEP association information available in our dataset. The distribution on the top right shows the linear speed of CMEs associated with SEPs. The bottom right shows the distribution of CME width. About 66% of SEP associated CMEs are halo in width. Because CMEs are followed by type 2 radio burst in the upper coronal region, they are used as an important diagnostic for predicting CMEs and SEPs. That is why we have included the information related to associated type 2 radio bursts in our catalog. There are 147 SEP events with identified type 2 bursts in the GSEP catalog. Let me wrap up the analysis part of my project with this summary slide. So overall, we find a good correlation between proton fluxes, the proton fluences, and the CME speeds. We have a moderate correlation with flare magnitude and a low correlation with CME width. We also find a low correlation between flare magnitudes and CME speeds. However, there is good correlation between CME speed and CME width. I have to mention here that CME data that has been CME data has been available only since 1996, and they are prone to projection effects. So furthermore, CME in situ measurements are not available in near real time. So future work that I discuss now onwards will not consider any CME data. So once we had the data set, once our data set was ready, the next step was to begin our experiments with machine learning models. So in this project, we used the GOES proton and X-ray fluxes as our input data. We implement time series based machine learning classifiers, and the task is binary classification, such that the target classes are large SEPs versus small SEPs. And we consider 65% of our data for training the model and 35% for testing the model. This work has been published in the Astrophysical Journal. We pick 3 classifiers listed on the left to compare the performances. So they are originally designed to handle univariate time series, and these are feature-based models. What they do is they extract relevant statistical features and representations from subsamples or intervals of the original time series. This is advantageous because in time series machine learning, one of the technique for improving model performance is reducing the dimensionality of the data by identifying and choosing the most relevant features. Here is a schematic overview of the workflow. We consider 3 proton channels and the long band X-ray channel from the GCP time series dataset as our input. We create a multivariate variant of the univariate algorithms using the column ensemble approach. So it is a parameter-wise ensemble of columns in which individual classifiers are applied to every parameter. So each univariate classifier subsamples the time series and extracts features from each interval to generate a feature data set and create a single output. We use the training set to train the models and extract learning curves. So these curves visually indicate the sanity of a model for overfitting or underfitting during the training phase. They also help us to understand how the model performance changes as we input more training samples. So the red line represents the training score, which evaluates the model on the newly trained data. The green line shows the estimators of the model on the samples used for validation, and the shaded area represents the standard deviation of the scores after running the model multiple times with the same number of training data. So remember that ours is not a big data problem. So even with such a small data set, we can see that the slope of the learning curves reduces after, for all the models at about 125 samples. So this is indeed an indication of satisfactory use of data or satisfactory data size. The next step is to evaluate the model performances on the test set. Remember, as I said earlier, ours is a binary classification task. So to do that, we consider the 2x2 contingency table, which provides estimates of true positives, true negatives, false positives, and false negatives. Using the contingency table elements, we can estimate model skill scores. So precision is used to evaluate the model's correct prediction with respect to false alarms. A recall characterizes the ability of the classifier to find all the positive classes. And F1 score can be estimated as the harmonic mean of precision and recall. Furthermore, we have true skill statistics or true TSS that can be used to compare the difference between the probability of detection and the probability of false detection. And lastly, the hierarchy skill score or HSS measures the improvement of the forecast over random prediction. So what I'm trying to say is we rely on multiple evaluation techniques and metrics in order to understand and develop confidence in the predictive capabilities of our models. So time to see the results from the test set. The receiver operating characteristic curve or the ROC curve. So these ROC curves are a diagnostic tool to evaluate a set of probabilistic predictions made by a model. So this plot helps us to visualize the trade-off between the true positive rate and the false positive rate at different classification threshold. Furthermore, we utilize the Uden index to find the optimal classification threshold. So here on the x-axis, the x-axis shows the false positive rate, and the y-axis shows the true positive rate for all the classifiers, and the dashed diagonal line indicates the ROC curve for a baseline or a no-skill classifier, and the orange line shows the ROC curve for the model. The quality of the model is then assessed on the area under the ROC curve or AUC. The intuition behind this measure is that AUC equals the probability that a random positive sample ranks above a random negative sample. And in this plot, the blue star in the upper left corner indicates the optimal threshold value of the model. In addition, the chosen classification threshold to estimate the model skills is provided at the top of the plot for each of the models. And what we find is that the area under the ROC curve for all the models indicates excellent discriminatory performance in all the classifiers. Here are the contingency tables for our models on the test set. So they are derived from the respective classification threshold I showed on the previous slide. What we can see is that the TSF and SCSF indicate a relatively higher number of false alarms, but the BOSS model outputs a fairly close number of misses and false alarms. So overall, the SCSF model fares better than TSF and BOSS. The table here shows the skill scores of the models. Even though the models take diverse approaches to generating the predictions, the outcomes are very close. And based on our multiple evaluation strategies, we find confidence in our approach and method. And although not directly comparable, we achieve far better results compared to the existing methods. However, I would like to remind you that we have used a data set with a closely balanced sample distribution, and the latency, that is the prediction window we have considered, is only 5 minutes. So the question is, can we do better? Of course, yes. So we take up the next project to add extensions to our approach and provide a proof of concept. So firstly, we want to include SAP quiet periods. That is because we want to introduce a natural class imbalance in the data set. Remember, in the very beginning, I mentioned that the number of SCPs observed near Earth is very few compared to the number of CMEs and flares. So to add SCP quiet periods, we consider large flaring periods that have not given rise to proton flux enhancements. So this follows a data-driven approach, and we will examine our best STSF model and 2 more baseline classifiers. And lastly, we examine multiple latencies from 5 minutes up to 60 minutes. And the results from this work is ready to be submitted to AppJ. So to choose non-event samples, we first look at the SCP associated flares in the GSCP dataset and find that less than C6.0 flares correspond to the bottom 15th percentile. So we choose that as our lowest magnitude. Next, we see that 70% of the SCP event onsets occur within 11 hours following an associated flare. So the idea is we add all the flares with magnitudes greater than or equal to C6.0 from 1986 to 2018. And next, we filter those flares that occur during an ongoing SCP event and remove all the flares within an 11-hour window. So with that, we finally have 2,460 additional samples for the negative set. I'm showing here the distribution of the entire data set with events and non-events. Just reiterating, there are 244 positive samples coming from the GSCP data set. For the negative samples or the non-events, we have 2,460 plus 189. And overall, we have a class imbalance of approximately 1:11. And each time series has a fixed observation window of 11 hours. And we split the data into training, validation, and test sets. So we use the training set to train the model, the validation set to tune the hyperparameters and compare the models. And we choose the best model to further evaluate on the test set. So the methodology is the same as discussed in the previous project, where we use an ensemble framework. So here is the performance of the models on the validation set. The plot shows TSS and HSS scores for all the models. And the different latencies in the bottom shows the x-axis shows the different latencies considered in our work. It starts from 5 minutes, then 15, 30, 45, and up to 60 minutes. So based on both the metrics, we can see that the STSF model performs significantly well compared to the other 2 baseline classifiers. So we chose the best model and estimated its performance on the test set. And here is the plot of TSS and HSS score at each latency. The average TSS score for all our experimental setup is about 0.86, and the slight variation in the scores between the latencies you saw in the previous slide and now is due to the subtle changes in the optimal classification threshold. So overall, what I would like to say is that our results give us confidence in our approach. So let me summarize the results of this project. So our goal is to develop a precise and accurate model for predicting SCP events. So we primarily use the GSCP dataset and extend our negative sample size by including SCP quiet periods so that the model can find discriminants between SCP and SCP quiet periods, SCP and SCP quiet patterns. And we implemented our earlier methodology of an ensemble of feature-based univariate time series classifiers. we consider a fixed observation window of 11 hours and use multiple latencies of prediction interval to leverage high fidelity for relatively low lead times. And based on our multiple evaluation metrics, we get some really promising results assessing our data-driven approach. Because our data set and sampling method are different, our results are not directly comparable with earlier works. And this project stands as a proof of concept of our modeling architecture. So the application we foresee for our predictive system are twofold. First, the system can serve as a convenient tool for forecasters at NASA SRAC, the Space Radiation Analysis Group, and NOAA SWEEPC, the Space Weather Prediction Center, in assisting them in broadcasting highly accurate SCP event warnings to astronauts on the surface of the moon or during extravehicular activities when outside the Earth's magnetosphere. And second, for future interplanetary missions, such as the missions to Mars that NASA is planning, the spacecraft will spend most of its time outside the Sun-Earth line. So therefore, the SCP predictions that apply to the Sun-Earth-Moon system are of limited value because the spacecraft, the Mars spacecraft and the Sun makes a large angle with the Earth-Sun direction. So to support the operational protocols, human mission on a journey to Mars would only have to carry a scaled-down version of a gauge-like instrument to produce short-term warnings of intense solar particle storms. So hence, we expect that our system can be a valuable addition to the tools that NASA will need to protect our astronauts on upcoming lunar and Mars missions. So in conclusion, my doctoral dissertation focuses on the development of a robust SCP prediction model. So for that, we follow a simple project life cycle from research to operations. In the beginning, I contributed to the development of an SCP dataset that covers 3 full solar cycles. Following that, I statistically analyzed to understand the relevant source solar features leading to SCP events. Next, I conducted machine learning experiments using time series models to classify between large and small SCP events. And then I worked on extending the time series ensemble methodology to include SCP quiet periods and establish a proof of concept for our method. So our immediate goal starting now is to transform the system to simulate them in a near real-time operational scenario. So let me take this opportunity to thank you all for being here and supporting me. With that, I end my talk and I'm open to questions.
All right. Thank you very much, Sumanth. That was a really nice talk. So anyone in the audience can ask questions now that Sumanth will answer. So make sure you unmute yourself before you answer your question.